Okay, let's continue a little bit more.
Okay.
We deal with the cylindrical coordinate. Cylindrical coordinate, you just need to change the axis, the coordinate system. With all this, you're very familiar with x, y, z, normal, tangent. By this case, we have the r, theta, and z. It's the same. It doesn't you change is a different way of communicating. So here you have a principal reference plane O, and then you have the R, you have a theta from the one of the reference axis here, theta, and the Z. Then you go into that particles, you split into three axes. Okay, you split into three axes. One is the radius axis. Okay, one is the radius axis. When you have this one, 11, I say. Okay, so three axes for cylindrical coordinates, three axes. So radius, theta, and z. Radius always go outside from the curve. R, radius means if you what you when you're describing a circle, right? You're mentioning the circle become bigger and bigger, how you define the radius always increasing, then the curve or the circle become bigger and bigger. That's why on the diagram here, the R is positive when you're going out from the curve. Right, the radius direction always pointing out to make the curve become bigger and bigger. And the Z, you know lah, Z is very direct. If that go up, then Z positive go up. And the theta. Theta in this case, be careful on the direction. Always anti-clockwise become positive. The theta is positive when you have anti-clockwise. Direction important, right? Same F equal to MA, but this time you're referring to R, theta, and Z. You group them in the same group. R means R, theta means theta, Z means Z. In this case, same. If the object moving on the plane do not move up and move down, your Z direction is 0. We have three set of equations when you deal with three-dimensional scenario, R, theta, and Z. So you have three sets. Same principle, F equal to MA, but different axes. Same idea, it was same idea with your X, Y, Z, a linear motion, tangent, normal, and B, same. Now we change the way we communicate. All right. Now, when do you know you need to use polar coordinate or cylindrical coordinate? When you are given theta in the questions. Reference axis theta and the R is given. Z is given. Sometimes Z just assume a 0 in the planar motion. So Z always sometimes 0. So you'll see theta and R, then you know you are using the cylindrical coordinate. Okay. This one you are very familiar. Meaning if you are giving an object moving in the blue line here, and there are force, external force pushing in, so this particle will move down. And according to coordinate, cylindrical coordinate, R is your position, theta is another position. So you are given some forces there. So you have F, P, and N. You have three forces here. So when you see forces, it means before under chapter 2, all forces equal to motion. F equal to MA. Change all the force become motion. Okay, so let's look at application. Same, but now when you look at the question, you know already. This one it will ask you to use cylindrical coordinate. You look at question, you are given theta, you are given r, you are given theta naught. Okay, now it seems like very complex, but actually don't confuse yourself. Right? So same procedure, right? You are giving a smooth. What I mean by smooth? No friction. 0.5 double collar can freely slide on the arm AB. If you move this arm AB, what happened to this one? This one can slide here and slide here, but it will still remain a circle. When you see circle, you know you have to use normal and tangent only. Okay, normal tangent, then call out the acceleration equation. Acceleration equal to normal acceleration plus tangent direction. An equal to v square divided by rho. At equal to time differentiation of your tangent velocity. Okay. Free body diagram. We are focusing on determine the force. Determine the force the arm exerted on the collar at the instant 45 degree. Means this one is 45. Free body diagram. Focus on the collar. Focus on collar. Straight away, you know that this one is cylindrical. Know that tangent normal axis. So I think you understand why normal pointing down. Because center is pointing down in this case. It's going inside. So your normal at that position, normal pointing down and not going up. Because this is a curve. Why tangent go positive to the left? You look at the diagram. Diagram here is anti-clockwise. Anti-clockwise. But we assume P is going to the right. Okay, then we add in equation, equation. Again, if you draw your P is on the left hand side, also can, but you'll get positive negative answer only. Then you need to flip the direction based on your free body diagram. But in this case, I just use P to the left. So I add in two more axes on the diagram, the radial direction and positive theta direction. Again, YR is pointing towards that direction. Radius become bigger, positive, so go up, positive. Why theta is pointing this way and not pointing down? Because the blue color arrow here. Blue color arrow here shift this way, so positive go this way and not this way. Okay. So you overlapping two axes. One is for the collinear motion. One is for the reference axis r and theta. Okay. Then you add in normal forces acting on the collar. Normal forces is the contact surface. Contact surface on the collar. In this case, I assume going down. And you draw going up, yes. But again, in your analysis, you will see negative if the direction is going down. Okay. Then there's a force from your AB, force AB, the arm AB. This one will pointing to this direction. Why MP this way? Because this is the arm, this one, always normal or 90 degree to that point. Right, this is the point, right? So it's a 90 degree to this pin here. All right, so FB, FAB. Then you start to solve F equal to MH equation. In this case, you are referring to R equal to MAR, and no longer we are focusing on T and N. You can do T and N, but you are missing a lot of information if you use T and N. The question already give you the R and theta, so you're referring to R and theta direction. So you group them, you put in the equation. For R, you solve using your free body diagram. In R direction, we do this way. So there's an angle here, 45 degrees. So here is 45 degrees. Okay, 45 degrees, then you split the forces, become negative something equal to 0.5 R. Same with the theta direction. In my solution, you see where is my positive. I give the positive value. For my R is pointing this way, positive. My theta is going this way, positive. I solve the two equations. Yeah, solve two equations. And then I update my kinetic diagram on the same free body diagram. I'm overlapping the kinetic diagram. AR that way, A theta that way. These are two vectors. You can find resultant acceleration. So this one you need to recall back. There is slides about this polar coordinate pattern. Okay. So in this case, you need to refer to Appendix C chain rules. Of course, in assessment, your test one or your final exam, you will not see Appendix C information. Right? So you need to use some. R dot is you use chain rules. Then R double dot also you get another equation. It's 45, right? Then theta dot will be that one. Theta double dot is 0. Then you substitute to get your R, substitute the angle here, substitute your angle theta dot, you get the R dot. And R double dot. Then you substitute. There is an equation for R, acceleration R as one theta. The one I ask you to memorize. When you come to polar coordinate one, right? AR equal to R double dot minus R theta dot square, and A theta equal to R double dot plus 2 R dot theta dot. This equation automatically come into your brain when you see the question give you theta dot. It will sure actually give you hints that you need to use this. You see theta dot with the question. Okay, substitution, you get the answer. All right. Then you find the missing parameter. Next one. Again, this polar coordinate in my class. Normally, this section will come when we do the test. First final exam question, I will not go into it. If you fail one time, then you need to retake. Then this one will come up. Means in my module, if you fail the first time, the second time will become harder and harder. So don't fail. So if you fail this object, then you need to study more.
So first time example, polar or
At this moment, no. At this moment, no. If you retest that, yes. You retake the final, then yes, you go.
so no need to study the all this polar.
I will brief you again when it comes to final exam. At this moment, as I know, no lah.
Okay.
Yeah.
Okay.
So don't fail. Don't fail.
So if we feel the next batch will turn design,
No.
different paper. theoretical method.
We test, then the normal one will be normal. Okay, so, but again, this one, normally I won't come up with this one. Normally I won't give this one. But you will see this one maybe in your assignment.
Test also
Test, normally I won't ask this one.
normally, yeah.
I won't torture you.
Normally, yeah.
I won't torture you. Normally, I won't torture you. Normally, I will help you in your test and assignment.
They torture us in final.
No. Final, normally, I will give you
Normally, yeah.
the tips. The tips.
Hey, I'm just helping you to summarize normally.
Unless the moderator say, hey, why don't you ask this question?
Yeah, normally.
Okay, but, yeah lah, but, yeah, I won't go into this. I won't go into this, R paper. Okay, the rest you will read on my slides. So, again, you see the steps. First, you always draw free body diagram and focus on that object of your interest. Don't confuse by the mechanism that we see. In this case, we are looking at the C, and you focus on C, and the challenges is the normal force when you deal with a round body. This one is your statics. Every time when you have a round body, only one contact surface is labeled as N with a 90 degree. So in this case, for point C, there's a force at here, pointing 90 degree. Alright, same with this one. F is this way because it's sliding on this axis, so it's 90 degree here. That's why F is here. Okay, you read now, example 8. Okay, with this, we conclude chapter 2. We go into chapter 3. I stop recording. Then I